Hello, everybody. I have the pleasure today to introduce our speaker, Dr. Tatiana from L'École Normale Supérieure of France. Dr. Tatiana studies at Lomonosov Moscow State University, where she specialized in the theory of algorithms and mathematical logic, brought her undergraduate degree followed by a PhD and ultimately a position as assistant professor in the newly created computer science department at Moscow's High School of Economics. In 2015, she took up a research associate post at Bristol University in England. In 2016, she becomes a postdoc researcher at University Paris Diderot. Since September 2017, she was associate professor in the Department of Computer Science at the Ecole Normale Supérieure of Paris, France. Dr. Tatiana is specializing in algorithms on strings as part of the theory, algorithms, graphs, and optimization team, where she is joined by Pierre Abulker graph theory and Chain-String Huang approximation algorithms. A key focus for the next 4 years will be her project on approximation and randomized string processing, which was awarded a grant from France Agence Nationale de Recherche in September 2023. The talk of our speaker today has as title, How Probability Helped Achieve Ultra-Efficient Algorithms for Pattern Matching. Thank you again, Dr. Tatiana, and please, you can start.
Thank you very much for the introduction and for the invitation. It's my pleasure to be here today, and thank you very much all for joining the seminar. So my talk will be somewhere in the middle between mathematics and computer science. I will only use a few definitions from computer science. You'll see that most of it is mathematics. At least this is what my background in mathematics says. And sorry, there is some weird echo. Okay, so if you have any questions at all, please don't hesitate to stop me. It will be I think it will be good to interact during the talk because I can only see black screens, and it will be a pleasure for me to answer some questions. But let's start. So today I would like to speak about a very basic problem of string processing, which is called the pattern matching problem, a very basic and very fundamental. In this problem, I'm given a short string. A string is just a sequence of letters. Letters can be anything. It can be letters of natural alphabet. It can be letters in the sense it can be some elements of a finite set, like, for example, a set of integers or even a set of words. So letters is just elements of a finite set, which we call alphabets. And string is a sequence of letters. In the problem of pattern matching, we are given a short string, which we usually call a pattern. We fix the notation for the pattern to be p, and we fix its length to be small m. And we are given a much longer string, t, which we usually call the text. And we fix the notation for the text to be t, and the length of t to be n. So what we must do? In the broad sense, we are required to output all positions in the text such that for some j between 1 and I, there is a substring t ji that is close to p. And it is for us to define what close means. On this example, you can see this long text, CAA, BC, AAA, etc. And the pattern is BC, AAAC. So what we can output the position 5, because you can see that the substring CAABC is close to the pattern BCAAC. We can output the position 9 because we see that the substring BCAAC is equal to the pattern. And we can output the position 20 because we can see that the substring ACAAC is close to the pattern P. But let us now discuss what close means. Let us try to formalize this notion. Of course, if the substring is equal to the pattern exactly, we can say that the pattern is close to the substring. But there are two other notions of distance between substrings that can be useful, that are standard in this setting. The first distance is the Hamming distance. It's only defined on strings of equal length. Like, for example, here you can see two strings, ser and cell. And the distance, the Hamming distance between strings of equal length, is defined to be the number of mismatching letters. For example, the Hamming distance between ser and cell is 2. The added distance is another very popular, very classic distance, and it is defined as the number of insertions, deletions, and substitutions required to transform the first string into the second one. For example, if you have two strings, Bora Bora and Barab, then the added distance between them is 4, because what you can do to transform Bora Bora into Barab, you can replace the first O with A, and you can delete the 3 last letters of Bora Bora in order to obtain Barab. And it's easy to see that with 3 edits, you cannot get Barab from Bora Bora.
Just a question, please.
Sure.
In the last slide, in the previous slide, please. The distance between ser and cell is equal to, because we have replaced the RR by LL. And
Yes.
if the position of RR be in the beginning of the word ser, the distance is also 2 or not?
Can you give me an example of?
The same example. For example, we start the ser by R.
So we take RS as the first word, at the first string, and LLS as the second string, right?
Yeah, yes, yes.
Yes, the Hamming distance will be 2.
Okay.
We only count the number of mismatching letters.
Okay, in the same position. Okay.
In the same positions.
Okay, thank you.
Thank you very much for the question. If it is clear, I would now like to formalize 3 variants of pattern matching that I would like to discuss today. So we are given a pattern, we are given a text, and we would like to output all positions in the text, such that for some substring TGI, either we have equality with P, with the pattern, or we have that the Hamming distance between the pattern and the substring is at most K for some fixed integer K, which we are given as an input of our algorithm, as a parameter of our algorithm. Or we would like to find all positions I such that for some TGI, for some substring ending at this position, the added distance between the pattern and the substring is at most K. All right, is this clear for now? Very good.
Yes, thank you.
So I would like to discuss the 3 variants of pattern matching today. But before I delve into the technical details, let me give you 2 examples of applications for this problem. The first example is a kind of an anecdote. In 1968, Jocelyn Bell-Burnell and her supervisor, Anthony Hughes, detected a very strange periodic signal. They were doing astronomy, and they thought at first that this was a signal maybe coming from aliens. Maybe that they thought that maybe aliens were trying to contact Earth. Of course, they soon realized that this was not the case. They soon realized that, in fact, it was the first experimental observation of a pulsar, a rotating star that emits beams of electromagnetic radiation out of its magnetic poles. And when the magnetic poles point towards the Earth, we can see this peak in the signal. And actually, pulsars play a very important role in astronomy, and detecting them is of fundamental importance. And if you have efficient algorithms for pattern matching, you can detect periodicity in streams. So this is the first application. And the second application is called read mapping. You might have heard about it, you might have not. So the idea is that recent methods of genome sequencing do not sequence an entire genome, because this is very expensive, this is very timely process. So what is done instead? The genome is chopped into small pieces called reads, and then like the physical process outputs this sequences of reads instead of the whole genome. And then, of course, one needs to assemble the reads into a full genome. And the idea is that if we have species that are similar, genomes are very similar as well. So what we can do, we can pick one genome that has been already assembled and call it a reference genome, and then try to detect substrains of this reference genome that are close to the reads. And this gives us the order between the reads. And then we can glue the reads together to obtain a new genome. And you can formalize this problem of mapping reads onto a reference genome as multiple pattern matching under edit distance. So we have to solve the k-edit pattern matching problem, but for many reads at a time. Okay? So I hope I convinced you that this is a fundamental problem with many applications. And let's now see what we can do in terms of theory. So our goal is to develop very efficient algorithms for pattern matching for the 3 variants of the pattern matching. And you have to know that in the classical approach, we assume that we are given the whole input at once. So we store the entire input, we store the entire text, and the text can be very, very long. Almost all classical algorithms for pattern matching assume that. So you have to use space which is linear in the size of the text. And the question that I would like to discuss today is whether we can do better in terms of space, whether we can develop algorithms with space that is sublinear in the length of n. And for that, we will consider a particular restrictive streaming setting, which was formalized by Alan, Matisse, and Starikovskaya in 1999. The idea is that the input is presented as a sequence of items. And at every moment of time, we receive just one data item. We receive just one letter of the text. We have to account for all the space we use. So if we use some letters of the text, we have to include it into the space complexity. It's a very restrictive setting, but this allows us to develop very efficient algorithms in terms of space. I will later return to this definition and I will make it more precise, but I hope that for now you get the general idea. When can we use this streaming setting? So I mentioned that the input is an output of a different algorithm. So we receive this output one data item at a time. This would be one setting where we can use streaming. Another setting is when the data actually comes from some sensor, like for example the heat sensor or the smoke detector sensor, and we receive like one measurement at a time, and then we can apply our streaming algorithm on top of that. Unfortunately, if we want to develop deterministic streaming algorithms for pattern matching for the 3 variants, I will show that we have to use omega of m space. So the question is whether we can do better if we allow probability. And the answer is yes. And I will show you this for the 3 variants of the pattern matching. So the first part of my talk will be devoted to exact pattern matching. Then we will discuss k-mismatch pattern matching, and finally the k-edit pattern matching. Let's start from the exact pattern matching. So I promised you to make the model a little bit formal. So here is the definition. We first assume we assume that first we receive the pattern letter by letter. We can process it and we can memorize some information about it. We have to account for the information that we memorize in the space complexity. So once we have processed the pattern, we can no longer return to it. We have no access to its letters. So from now on, we can only work with the text. And we receive the text also as a stream, one letter at a time. And when we receive a letter, we must say whether there is a substring that ends at this letter and is equal to the pattern. So for example, when we receive this letter A, the answer is no. Then we receive another letter A, the answer is still no, because A, B, C, A is clearly different from the pattern. We receive another A, the answer is still no. Now we receive a C, and the answer is finally yes, because we have B, C, A, C as a substring of the text, and it equals to the pattern. And then we receive an A, and the answer, again, no. Okay, So is the problem and the setting clear?
Yes, thank you.
Great. So let us first show that if we want to develop a deterministic algorithm, then we have to use omega of M space. Recall that M is the length of the pattern, okay? And this is done by a simple counting argument. I assume the binary alphabet, so I have only 2 letters in my alphabet, 0 and 1. And let's assume that N is equal to M. So there are 2 to the M different patterns that I can have. If we use less than M bits of memory, it means that there are 2 patterns, P1 and P2, which are different, but for which the states of the memory of the algorithm are equal after reading them. Okay? So recall that first we receive the pattern, we pre-process it, we memorize some information about it, and then we can no longer return to the pattern. So we have read P1 and P2. We are in the same state of the memory. Now we receive the text. Let's take the text equal to P1 in both cases. Then for P1 and T equal to P1, the answer must be yes when we receive the last letter of the text. And for P2 and T equal to P1, the answer must be no, because P2 and P1 are different. But this is impossible because after reading P1 and P2, the algorithm is in the same state of memory. So the algorithm cannot distinguish between P1 and P2. And then it receives the same text in both cases. So what it means? It means that if we want an algorithm that uses space sublinear in M, we must use probability. We don't have another solution. So let's see what we can do. If you have ever studied algorithms for pattern matching, you might have heard about the K-priming algorithm, one of the classical algorithms for pattern matching that uses probability. If you haven't, this is not a problem because I will remind you of the algorithm right now. This algorithm uses a hash function, which is defined as follows. So if I have a string of length M, S1, S2, Sm, then the K-priming fingerprint phi is equal to the sum from I equal to 1 to M of Si times R to the power M minus I modulo P. So here P is a prime, a large enough prime. I will say a few words about this later. And R is a random remainder modulo P. So you can see it as a value of a polynomial with coefficients equal to the letters of the string. So here I assume that the letters are integers and evaluated at point R at the random remainder modulo P. Okay. So I claim that it is a good hash function. What does it mean? First, it's easy to see that if I have 2 strings of length M, then necessarily their fingerprints, the value of the hash function, is equal for them. But it can also be shown that if the strings are different, then the fingerprints are different with high probability, if I choose the prime P large enough. Also, this hash function is concatenatable. What does it mean? This is a very important property. It will be important for us later. So I would like you to memorize it. So if I'm given 2 of the fingerprints, phi of x, phi of y, and phi of xy, so xy is simply the concatenation of strings x and y, then the third fingerprint can be computed in almost constant time. Constant, maybe with 1 log, okay? So once again, if I'm given the fingerprint of x and the fingerprint of y, I can compute the fingerprint of xy. If I'm given the fingerprint of x and the fingerprint of xy, I can compute the fingerprint of y, right? And this will be a property that will be important for us later. So now let us develop our very first probabilistic algorithm for pattern matching.
Sorry, Tatiana, can you go back to the previous slide? And when you mention a linear complexity, so it is with respect to the size M. The big O of 1 time, it's it's with respect was the sum of the size of each x and y. It is m. It is what?
It's actually log m. It's because you need, so when you want, let's assume that you have the fingerprint of x and the fingerprint of y, and you want to compute the fingerprint of xy. I don't know if it's easy to see it, but actually what you need to do, you need to multiply the fingerprint of x by an appropriate power of r, and then sum the two things together. So the only thing that takes you more than constant time is computing this power of r. And this power of r, it's never bigger than the length of xy.
Okay, so the idea is that you have a string of length m. The fingerprint will be then more or less of length log m, so which is more or less possibly the size of piece that you need for this. The sum will be of complexity, could be of complexity log m, but in fact, no, your fingerprint is good and you just need big O of 1 and not big O of log m. This is what you mean?
Let me say it again. So I claim that in order to compute the fingerprint of xy, the only thing that you need to do is to multiply the fingerprint of x by an appropriate power of r, and then sum it with the fingerprint of y. So the only thing that can be costly is computing this power of r. And this can be done by standard explanation, like you double the power of r every time. And it can be done in time which is logarithmic in the power that you need to compute.
Yes, so it seems to me that there is no long carry property. When you add numbers, sometimes you could have a carry, which is...
No, okay, yes, I understand what you say. So let me go, like, I'm going to say something which is quite technical. If you don't understand what I say, it's not a big deal. So actually, like when we speak about, at least when I speak about algorithms, it might be different. I use the word run model of computation. It might be different from the model that you are used to. In the word run model of computation, we assume that integers every...
Sorry, what is it that you said?
So I work in the word RAM model of computation. It stands for random access memory machine. And in this model of computation, what I assume that every integer is stored in a machine word. And then there are some elementary operations that I can do in constant time. For example, I can take two integers and I can sum up together these two integers in constant time. I can multiply two integers together in constant time. Division is constant time as well. So it's a very simple model of computation. I do not take into account any overflows or anything like that. I assume that I have enough bits in my machine words in order to be able to do the computations like that. I assume that I never work with very large integers, and I assume that I don't have this problem of overflows. Basically, every simple arithmetic operation is in constant time, like plus, minus, division, multiplication is in constant time in this model.
Okay.
I hope this explains a little bit. All right. So it's a simplification, of course, I agree, but it allows us to evaluate complexity, and it gives us some understanding of how costly an algorithm is. So let us see what we can do using these K-prime fingerprints. The idea of the K-prime algorithm is very simple. We compute the K-prime fingerprint of the pattern, and then we compute the K-prime fingerprint of every m length substring. So once again, m is the length of the pattern. And we compare the fingerprint of each substring of length m with the fingerprint of the pattern. If the two are equal, we output the last position of the substring. We say that it's a position of an occurrence of a pattern. This is what we say. And let us see why the algorithm is correct. It's correct because we have this property that the hash function, the car-private fingerprint, is good. So we know that if the fingerprints are equal, then the strings, the substring with high probability is equal to the pattern. So we cannot do too many mistakes. The only thing that I have to discuss is how to compute the fingerprints of the substrings. I can compute the fingerprint of the first substring of this, which starts at position 1 and ends at position m in big O of m time. This is because I need to evaluate this polynomial, and it can be done using this standard scheme. And now to compute the fingerprint of the substring that starts at position t minus m plus 1 and ends at position t. Here you have the definition. I can compute it from the previous fingerprint, from the fingerprint of the substring that starts at position t minus m and ends at the position t minus 1. I can do it using the following simple recurrence. I can say that this is the fingerprint of the substring t minus m t minus 1 minus t minus m times r to the power m minus 1 times r plus t modulo p. Okay, so you can see that.
Tatiana, again the question. Are you adding some log m factor somewhere or not? Because when you say computed in OM time, so I understand what you said with the RAM, the step 1. In fact, I am already worrying here. You said that you were using the RAM model. Okay, so sum and product is constant time, but then you had a sum of length m, okay, so big O of n, but then you had your powers, which a priori could take some up to I don't know, log m time or something like this. I don't remember what were exactly the exponent. Yes, so it's r to the m here. So a priori, I would expect m times log m for the.
So in fact, in the first step, we don't need the log m. Why? Because we compute t1 modulo r, then we multiply it by r and we add t2. Multiplied by r and add t3. Yes, exactly.
Thank you.
And for the second step, yes, this tilde here, it hides the log m. This is quite recent in theoretical computer science. I agree this is not a perfect notation. Sometimes it hides many logarithms. Here it hides only one. You can actually remove this logarithm. It's not necessary, but for simplicity, let's assume it's there, okay? And this is, yes, to compute this power of r. Okay? And you can see that you need only a constant number of such operations. And because of that, we need tilde of 1 time to update the fingerprint. So in terms of time, the algorithm is very efficient. It takes this log m time per letter of the text, or in total, it takes n log m time. But let's discuss the space. You can see that in order to update this fingerprint here, you need to know t minus m. This is a letter that is m positions before the current letter t. Okay, so you need to be able to access a letter that arrived m positions ago. And unfortunately, you cannot do this otherwise, but to store the last m letters of the text. And it means that the car-private algorithm needs omega of m memory. So yes, it uses probability. It's very efficient in terms of time, very simple, but it needs omega of m memory. Let's see if we can do better. So actually, the first algorithm which managed to break this barrier of m memory was the algorithm of Port and Port from Fox 2009, almost 30 years after the algorithm of Kaplan Rabin. They showed an algorithm with log m space and log m time per letter of the text. Then it was a little bit improved by Breslau and Galil. And then we also showed generalizations of this approach for the case when we have not just one pattern, but dictionary of patterns. And there is actually one interesting open question related to these results. Here, the space is in words, it means that actually we use log squared m of bits. And all known low bounds say that we must use omega of log m bits. But we don't know where the true complexity is between this log m and log squared m. Let me now show you some ideas behind the algorithm of Poret and Poret. One important brick in the solution is this following combinatorial lemma. Let's assume that you have two strings, y and x, and let's assume that the length of y is 2 times the length of x. I claim that either y contains at most 2 occurrences of x, it means 2 substrings that are exactly equal to x, or the occurrences form an arithmetic progression with difference equal to the smallest period of x. What is the period? It means, like, for example, if you have a string ABC, ABC, AB, the period is equal to 3. It's the smallest shift, such that when you shift your string by the period, you have an equality of the string and its shifted copy. So let us see how this regularity of occurrences help us to develop an efficient algorithm. Here is the algorithm. You can see that it's not very complicated. The idea is that you have your text T and you store log n level of occurrences. You store occurrences of the prefix of the pattern of length 1 in the text, occurrences of the prefix of length 2 in the text, occurrences of the prefix of length 4, and finally occurrences of the pattern itself. And now every position of the text is tested log m times. First, you test whether it's an ending position of a substring which is equal to P1. Sorry, vice versa. First, you test whether it's the starting position of a substring that is equal to P1. Then you test whether this position is a starting position of a substring that is equal to P1, P2. Then to P1, P4, P2, P3, P4, and finally to the pattern itself. So you can see that if a position in the text is actually the starting position of a substring that is equal to the pattern, it will pass all the tests, right? So for now, it might seem that we do more work than in the algorithm of Cup and Robin. But let's see how it helps us to reduce the space complexity. So this is how we implement this basic idea. When we receive a position Ti, we check whether it equals to P1. And if Ti is equal to P1, the first letter of the pattern, we push I to the level 1. And then we do the following for each level. We take the leftmost position in the level. We check whether the distance from this position to the current position of the text is equal to the length of the next prefix. And if this is the case, we check whether there is the next prefix at this position, whether there is an occurrence of the next prefix at this position. And if so, we promote the position to the next level. If there is no occurrence of the next prefix at this position, then we simply discard it. So you see that the algorithm is correct. It will have to pass all the tests. If a position will have to pass all the tests if there is an occurrence of the pattern at this position. And it's a bit tricky to understand why it can be implemented in small space. Let's see. So in level J, we store occurrences of P1, P2, P2 to the J in the last 2 to the J plus 1 letters of the text. And we know by the combinatoric lemma that I showed you in the very beginning that either there are at most 2 occurrences of this prefix in the last 2 to the J plus 1 letters, or they form an arithmetic progression. And an arithmetic progression is good. It's very regular. You can store an arithmetic progression using constant space. It's enough to store the first element of the progression and the difference, right? And this regularity also helps you to test positions very efficiently in constant time. So for each leftmost position in each level, you only need constant time to check whether there is an occurrence of the next prefix. And this is due to the regularity of occurrences and this important property of fingerprints that I asked you to memorize, the concatenability. Okay, I don't really want to explain the details, but this can be done. So in total, for each level, we need constant space to store the arithmetic progression and some extra information. And we need constant time for updating each level when a new letter arrives. In total, we need log m space and log m time per letter of the text. And the algorithm is correct with high probability, which comes from the fact that if you have two distinct strings and their fingerprints are equal, this can only happen with a small probability. Okay? So this is all I wanted to tell you about exact pattern matching in small space. If you have any questions, you can ask them now. And if not, I will pass to the k-mismatch pattern matching. Okay, let's go to k-mismatch pattern matching. If you got a little bit lost with the exact pattern matching, you can come back now because this will be quite independent from what I have said already. So let me once again start from the model. We assume that the pattern arrives first. We can pre-process it and we can memorize some information about it. And then we can no longer access the pattern. We can only access the text, which arrives as a stream one letter at a time. And when we receive letter T of the text, we must say whether the Hamming distance between the latest m-length substring and the pattern is at most k. And otherwise, we can simply say, no, the distance is too large. Okay, this is our problem in the model. And let me start once again by showing that any deterministic streaming algorithm for k-mismatch must use omega frame space. I will actually take k equal to 1, okay? And assume once again the binary alphabet, so we have two letters, 0 and 1, and assume that n, the length of the text, is equal to m, the length of the pattern. There are 2 to the m different patterns, and if we use less than m minus log m plus 2 bits of memory, it means that there are m plus 2 patterns for which the states of the memory of the algorithm are equal after reading them. So we can run the algorithm for each pattern pi and the text t equal to p1. Now there are m plus 1 strings at the Hamming distance at most 1 from this text t, and that means that at least one of the answers must be different. But this is impossible because the state of the algorithm was the same after reading all the PIs. And it means that if we want sublinear space, we must use probability. Okay? And this is the results that we have for k-mismatch pattern matching. We have the first algorithm with a space complexity that is sublinear in M was shown in the same seminal paper of Porat and Porat. They showed an algorithm with k cubed polylog n space and k squared polylog n time per letter. Then it was subsequently, the space complexity and the time complexity was subsequently improved in a series of results. And the current best algorithm uses k polylog n space and square root of k polylog n time per letter. So let's see how we can achieve this type of complexity. And let's start from a puzzle. Let's assume that we have two strings. I want to compute some information about the first string and some information about the second string to be able to tell if the Hamming distance between the two strings is equal to 1. This is how I can do that. Let's partition the two strings into substrings of q colors. So you can see that I partitioned the string 1 into a green string A, the red string B, C, B, B, and the white string A, B, A, B. And I partitioned string 2 into a green string A, C, A, into a red string B, C, B, A, and into a white string A, B, A, B. And they are equispaced. So the distance between the letters in every substring is equal to q. Now I claim that if I have exactly one mismatch between the first string and the second string, it means that there is exactly one pair of substrings that does not match. And now I hope that if there are at least two mismatches, they will end up in substrings of different colors. And it means that there will be at least two pairs of substrings that do not match. And I hope that this will help me to distinguish between the two cases. So let's see if we can implement this. We take all the primes between log m and log squared m. And by the prime number theorem, there are at least log m such primes. Okay? Now I partition the first string into, for each q, I partition the first string into q equispace substring, and I partition the string 2 into q equispace substring. Now let me prove that if there are at least two mismatches between string 1 and string 2, then there exists a prime q among those that we have selected, such that at least two pairs of substrings do not match. What does it mean that the mismatches are in the same pair of substrings? It means that the distance between the mismatches must be equal to 0 modulo q. But the distance between the mismatches is at most m. So it cannot be a multiple of log m distinct primes. And it means that at least for one prime, we'll have that the mismatches end up in different substrings. Now I can solve the one mismatch pattern matching in the following way. For each position of the text and for each prime q between log m and log squared m, I compute the number of subtexts, substreams, and subpatterns that do not match. And if this number is equal to 0, I know that there are no mismatches between the text and the pattern. The Hamming distance is 0. If the number of mismatching pairs is bigger than 1, then by the lemma that I showed you, I can say no, the Hamming distance is too large. And otherwise, I return yes, the Hamming distance between the pattern and the text is equal to 1. So I need to explain how we compute this number h here. And for that, we do the following thing. We reduce the one mismatch problem to exact pattern matching. I partition this pattern into substrings. I partition the text into subtexts. And then for each subtext, for each substream, and each subpattern, I run the stream in exact pattern matching that I showed you previously. And this gives me the following complexity. So the space is the number of primes, log m, number of substreams for each prime, which is log squared m. You remember that the primes are bounded by log squared m. The number of subpatterns, which is also bounded by log squared m, times log m. This is the space that I need for exact pattern matching. And the time is log m, log squared m, log squared m. So you can see that the space and the time are polylogarithmic in m. And if I have not just one mismatch, but a arbitrary number of mismatches, then by repeating the same idea, but with more primes, I can achieve k cubed space and k squared time streaming algorithm for k mismatch pattern matching. This idea was also used in Clifford et al. And the Golem topology and Porret, which you probably saw in the table. They have a little bit better complexity. But the current best algorithm uses a completely different idea. The idea is to use a new hash function, which is called the k-mismatch sketch. It's defined as follows. It's tuple. It consists of the k-prime fingerprint that we have seen previously, and of the expressions of the following form: phi0s, which is equal to the sum of si's. This is the letters of the string s modulo p. Phi1s, which is the sum of si's, but times I modulo p. And the last expression is phi2ks, which is the sum of si's times I to the power 2k modulo p. So here, once again, p is a prime and r is a random integer in 0p minus 1. Clifford, Kachimaka, and Porret in Soda 19 showed that if we're given the k-mismatch sketches of two strings, then we can decide whether the Hamming distance between the strings is at most k and big O of k time correctly with high probability. This is the idea. Suppose that we have k prime, which is at most k, mismatches between S and T, and x1, x2, xk prime are the positions of the mismatches. Then what we have, we take the two sketches and we compute the difference phi0s minus phi0t. This will be equal to this expression here. Then phi1s minus phi1t, phi2ks minus phi2kt. This will give us this system of equations, and this set of equations is very similar to those appearing in the decoding procedures for Reed-Solomon codes from the error correcting field. And one can use the techniques from 1980s to find x1, x2, xk prime. Another important property of these k-mismatch sketches is that they are concatenatable. And due to that, one can use the exponential prefix approach, the one that we saw in the exact pattern matching, to achieve a tilde of k space, tilde of k time algorithm. I will not give any further details here. I just want to finish my talk by quickly show you the results that we have for the added distance pattern matching. So the setting is that we want to find all positions T in the text such that for some substring ending in this position, the added distance between the pattern and the substring is at most k. And here are the algorithms that we have. So the first algorithm was given by myself in 2017. It was a rather stupid algorithm. It had a horrible complexity of square root of m poly k, and the time complexity was not great either. It was square root of m poly k per letter, but it was the first sublinear space algorithm for k-added pattern matching. And subsequently, we improved the complexity to tilde of k to the 5 space and tilde of poly k time per letter. And then in 2023, Podhachuriya and Kutsky showed an algorithm of k squared space and k squared time letter, ignoring the polylog factors. I will not probably give you the technical details because I can see that we are running out of time, but I want to tell you what is the main challenge for developing such algorithms. The main challenge is that there are no concatenatable sketches for the added distance, and this is something all the three papers had to overcome. So let me stop here. I will be happy to answer any of your questions, if there are any.
Thank you, Dr. Tatiana, for this nice talk. Please, are there some questions?
So yes, possibly on your slide, so it was 14. You had some discussion on some log or log square, and I wonder if there was a typo or because yes, here you said that we don't know where is the right order or something like this, and you mentioned some log iterated log square, but by showing the last one, which was in fact log m, so I was not sure of what you meant.
So here the space is in words, and in the word-round model, we assume that every word contains log m bits, theta of log m bits. So it means that if I measure the complexity in bits, sorry, it creates lots of confusion. It means that if I measure the complexity of this algorithm in bits, they use big O of log squared m bits of words. This is because we have to, so you remember that we have this exponential, a logarithmic number of levels in our algorithm. And for each level, we have to store a number, which takes log squared m bits. Sorry, which takes log m bits. So in total, the total complexity is log squared m.
Okay, so this was the square, which I was not seeing on the slide.
Yeah, sorry. And the lower bounds that we know are omega of log m. So we have this gap, and we don't know where the true answer is.
And for the edit distance, I don't remember if you had a similar slides at the end or not. Or what is the current state of what is done?
So the current state is that we have an algorithm with tilde of k squared space and tilde of k squared time per letter. There are many, many open questions. So the first is that we do not know what is the optimal dependency on k. Do we need to use a k squared polylog m space? Is k polylog m space is enough? We don't know.
Tilde O is log m or a polynomial in log m?
Polynomial in log m, yes. There are like many log m factors that are hidden.
Okay.
I agree this is not a perfect notation. It's just to make the complexity a bit nicer. And then in terms of time, we also don't know. I think that the time should definitely be, it should definitely be possible to improve time, because what we know that if we want to compute the added distance between two strings of length n, we must use n squared time under a widely believed hypothesis. There is a low bound. So if you have two strings of length n, then you have to use n squared time to do that, okay? And so if you want to compute the added distance, but if it's bounded by k, you can say that the optimal complexity, time complexity you can hope for is nk. Here, the total time complexity is nk squared. So 1k extra. So my hope is that this time complexity can be further improved to k.
And all what you presented is for some models with one CPU, one memory. If we try to parallelize it or to distribute the computations, is there some interesting phenomena which are popping up?
So I'm not an expert in parallel computation. What I can definitely say is that if you have this streaming algorithm, and for example, if you work with the dictionary of patterns,
yes, then it's natural
to parallelize the computations. And what is important to know is that actually you don't have to repeat the algorithm. If you have d patterns, then you don't have to repeat the algorithm for one pattern d times. Like, for example, let me show you, let me go back to this, probably to the exact pattern matching. So here you can see that if we have d patterns, then we can find the occurrences in the text in space d log m. So the space is still the space for one algorithm multiplied by d. But the time complexity is not d log m, it's log m plus d. So we don't have to repeat the algorithm for the single pattern d times in order to obtain an efficient algorithm for a dictionary of d patterns.
Oui, bonjour, professeur. Oui, ça va mieux.
Attention, votre micro est allumé.
Oui.
Ok, je suis ici même au labo.
Okay, so
Sorry.
I try to cover with
D'accord, ok.
in parallel.
Okay. It's okay.
I can't hear anyone. So Cyril,
It's okay now?
I think it's good, yes.
Okay. Cyril?
Okay, sorry. Yes, I was saying that this log of m plus d is, let's say, surprising. So is there a quick explanation of the idea behind it?
Yes. Let me think how to explain it. So what we actually do, we consider three types of patterns. Patterns that are shorter than log m plus d, and patterns that are longer than log m plus d. And for those short patterns, we built a data structure. It's called ZFastTry. It's basically a data structure that allows to store strings, a set of strings. And you can ask dictionary lookup queries to this data structure.
Mhm.
You can ask whether some pattern is inside this data structure, whether some string is inside the dictionary of short patterns. Okay, and there are two implementations of a try. There is a deterministic implementation, but then you have to pay the length of the pattern to decide the length of your query string to decide whether it's in the dictionary. And there is another implementation, probabilistic implementation, which uses Kapp-Rabin fingerprints by one of the authors is Jamal Belozogui, but I don't remember the other authors, sorry. And this implementation, it allows you to decide whether your query string is in a dictionary in a log the length of the pattern time. And the idea is that you use some kind of a binary search to do that.
All of this is okay. What is not very clear is the M plus D. Is it the idea of the max and M and D? It was a shortcut for this, or it's really M plus D?
It's M plus D, yes. I don't remember where it comes exactly from. Sorry.
Mm-hmm. Okay, thank you.
Okay, thank you, Cyril. I have a question, maybe a general question. It's possible to use some known results on Emery trees to study this pattern matching problem, where M is exactly the number of letters that you use. And the distance will be between the pattern and any other word will be the distance between the two nodes in this tree.
Mm-hmm. Maybe, but
okay.
The question is the space complexity.
Mm-hmm. Okay.
So I presume that if you want, like, if you have all the nodes corresponding to substrings, then the space complexity will be linear in size of the text.
Okay, thank you. Other questions, please? So if not, we have to thank again Dr. Tatiana for this nice talk, and we see you next week, 1st October, with Dr. Vanji Fang from the University of Gustav Eiffel, which with a talk with title Tamari Intervals and Blossoming Trees. Thank you to all. Thank you, Tatiana, for
Thank you.
your talk, and see you next week. Bye.